Okay, so Olga is now in Vienna, and so she made I had the chance that she made the PhD with me in Sorbonne University. And she will speak about gradient flows on neural network manifold. C'est ça? Ouais. To be or not to be. Wow.
Thank you, Yvon. It's a great pleasure to be here. Thanks a lot for the invitation. I feel very honored. And I am very happy to present today this work. I would like to say that I'm very excited about this result. It has taken my group about 3 to 4 years to develop this result, and the draft is about to come out in maybe 1 or 2 months. It's a result about this time-dependent parametric approximations, which are usually now involving neural networks because it's very versatile. And by now, this kind of technique, depending on the community, is going to be called neural Galerkin, dynamical approximation, or if you apply to gradient flows, people from machine learning and optimization have coined it as a natural gradient flow. So this talk is about all these kind of keywords, and it's about actually a deep existential question, which is about the existence of the curves that are going to be defined by these dynamics. So the goal is going to be, I think I have to start writing from here because it is going to maximize the amount of people being able to see the blackboard. So the goal is that we are interested in the dynamics of solving in fact in a Hilbert space, which is about to become very quickly only L2 of R, a gradient flow given by this type of dynamics, where f is going to be a function from my Hilbert space to R. It's going to be my energy function. And then this type of dynamics is going to arise, for example, when we want to model a certain physical system that has some gradient flow structure, or the problem also arises when I want to minimize this energy. And so a prominent example nowadays is if I want to minimize f of v for v in my Hilbert space, and then if I apply a gradient descent technique expressed in continuous time, this is going to be this type of evolution. And in fact, the problem numerically is that I am in an infinite dimensional space, and I cannot really solve it fully in here. I need to introduce some proxy to approximate my solution. So this v is very quickly going to be replaced by some vn, where I am going to parameterize a family of functions with n degrees of freedom, and everything is going to take place here. So in this talk, Vn is going to be generated by neural networks, and the spicy thing about them is that they are over-parameterized. Okay, so the main difficulty is going to be to define trajectories within this set of this form, such that everything is mathematically well kind of principled and guaranteed. And so I'm going to establish a certain language to speak about these neural networks, and I am going to call them, I want to convey the idea that these are non-injective decoders. Okay, so For me, a decoder is going to be a mapping phi from a parameter space theta to my ambient space V. And the problem with this, okay, so here's an example. The prominent example I am going to kind of look at all the time is going to be a shallow neural network of this form, the sum from 1 to n of some coefficients sigma I times sigma AIX plus BI. And I am already restricting my language to this space, L2 of R, where X is only in dimension 1. I'm doing this because the results we have only hold for this dimension so far. Okay, so these are going to be my parameters. These are going to be theta equals AI, can you still see here? AI, BI, CI for I equals 1 to n, and this is going to belong to the space capital theta, which is going to be R3 n in this case. Is this clear for everyone so far? Okay, so in this case, so I go from R3n, my parameter space, to L2 with this ansatz. And the Vn that I have introduced over here is going to be the image, it's going to be the family of functions that I'm going to generate when I vary the values of my parameters. So it is going to be phi of capital theta, or in other words, the family of phi of thetas when I make theta vary in my ambient space of parameters. Now, this, it is very compelling to think, okay, so this is a parametric approximation, so this looks like a manifold. It looks like a manifold, and almost for everything, it is going to behave like a manifold. So if I assume that sigma is C infinity, no problem of differentiability. So, my mapping here is kind of differentiable in the parameters. Everything is fine. But what happens? The problem is that I have over-parametrization here, meaning that there can be several kind of choices of parameters that are going to lead to the same function in the end. And so this is going to translate dramatically into the tangent space of this object, which I am going to call this way. So the tangent space at what? Excuse me. So the tangent space at a given function of my family of Vn. In fact, what is it going to be? So if now I see this as a manifold, in fact, it is going to be given by the span of the partial derivatives of phi of theta from 1 to, okay, so here I have 3n, okay, so I have to go here till 3n. And so what happens? Suppose, here's the gig. Suppose that phi of theta is of this form. I have exponential minus x minus theta 1 square plus exponential minus x minus theta 2 square. Now, the tangent space in this example is going to be the span of the partial derivative with respect to theta 1 and the one of theta 2. So it's going to be something like this. It's going to happen x minus theta 1, comma, the same for theta 2. Good, so far so good. Now, what is the dimension of this space? So this space, by the way, is going to be included in my ambient space. And what is the dimension of this thing? Well, in fact, when theta 1 is equal to theta 2, this is going to be a space of dimension 1 only, is equal to 1 if theta 1 is equal to theta 2, and the 2 otherwise. Okay, and so this is because when theta 1 is equal to theta 2, somehow I am going to generate essentially the same function, right? So this is going to be a function with 2 bumps, morally, and then so if I make them coincide, I am only having 1 bump. And so if on top of it I add here coefficients, so we see that for theta 1 equals to theta 2, so I am kind of factoring out these coefficients and I'm sort of generating all the time the same function, but I can generate it with different values of C1 and C2. So there's kind of this degeneracy, which is going to translate at the level of the fact that the dimension of the tangent space is going to change. Okay, and so the change in this tangent space is precisely the thing that makes this kind of object not a classical manifold from Riemannian geometry, because in Riemannian geometry, if I have 3n parameters, the dimension of my tangent space is going to be equal to 3n. But here, it is going to be degenerate at some point. And in these points, in fact, my mapping is not going to be injective, because there are going to be several types of parameters that are going to generate the same function at the end of the day. So that's a problem I sort of, okay, so everyone is aware. And so here is how all this neural Galerkin stuff and so on is going to sort of fail in the theory because of the presence of this thing. So now, what is going to be my strategy for solving my original problem with functions from this space? The strategy is, okay, I'm going to call this dynamical approximation. The strategy is that I want to approximate u of t by a decoder whose parameters are going to evolve in time, okay? And so this idea, I saw it for the first time in one of Benjamin's papers, and I found it absolutely wonderful. And I got completely converted to it and passionate by it. And so also because I became obsessed by this thing that is going to happen, so this is the ansatz, and then we differentiate, we take the time derivative, and what we hope is that the time differential of this one is also going to be a good approximation, and the differential of this is going to be this thing over here, scalar product theta dot of t. And now the kind of very beautiful idea underlying all these schemes is that instead of approximating the state itself, we are approximating the velocities by saying that my ansatz, this is d phi theta dt at time t. So I want that, in fact, this guy, well, let me write it in this form. I want that this guy, which is the velocity that I can compute, is close to the exact time derivative, which is this one, which is minus the gradient. So I'm going to assemble a residual here, which is saying plus the gradient of f applied to phi of t in the v norm, and I have to minimize over theta dot for every time. So here, in fact, the unknown is going to be my velocity. So in order to reflect on this, I'm going to kind of change my notation and say, okay, this is my unknown, and I'm going to call it eta dot, and the one that minimizes is going to become my theta dot of t. This is going to give me the direction in the parameter space that I have to follow in order to make the velocity residual as small as possible and mimic as much as possible this equality. Okay, so this eta dot, in fact, it is in our setting, it is going to live in R3n. Here now comes a curveball. The optimality conditions for this system are leading to a very compelling ODE system of equations for theta dot, which is going to be of this form, where M of theta t is a matrix of the cross products of the parameters of the parameter inner products, and Q of t is somehow reflecting the projection of the gradient term into the space generated by the span of these partial derivatives over here. And so this is a vector here, from I equals 1 to 3n. Okay, so yeah, this is a matrix with indices ij ranging for all the parameters theta I that I have to take. Okay, so this is like a gram matrix. It is the gram matrix of the tangent space of these elements, which I'm seeing now as basis elements, and it is appearing in this system of equations over here. And then the fabulous fact is that you can assemble at every time step. You can then do some time integration here to retrieve theta at time tn plus 1 at the next time. You get phi of tn plus 1, theta of tn plus 1, you plug it to the phi, and then you get your approximation and your next step, right? So this leads to a very kind of clear pathway to get your solution phi of theta t. So here's the problem. The problem is that to solve this in continuous time, this matrix at the locations where this is degenerate, this matrix is not invertible. Yeah. Obviously. So this is kind of obvious to everyone, but it is not at all obvious how to solve the problem properly. Okay, so here are like the suggestions that you can find in the literature. If you add some regularization term here of this type, for example, you put here regularization of the type epsilon over 2, norm of eta square in R3n, for example, you're gonna get here some regularization term that is going to pop up and which is going to be of this form, for example. Okay, fine. But personally, I am super unhappy because if you solve this, the problem is that you are deviating from the true dynamics that you wanted to reflect, okay? So you cannot really control what is happening anymore. How can you connect what you're getting with your original dynamics over here if you have put some regularization parameter? And okay, you can always tell me, yeah, I make epsilon as small as possible, I make dt as small as possible, but can you guarantee that the curve that you get even exists? And the problem is that to guarantee existence of the continuous curve, at the end of the day, when epsilon goes to 0, you're gonna be facing the same problem that this ODE here is not well posed. And one can try to analyze it with the optics of differential algebraic equations, for example. So we took a book of this, and then, I mean, after 1 hour, we just threw it to the trash can, because so that theory knows only how to kind of do certain limited things when the degeneracy is that we lose one dimension here, essentially, and sometimes 2 dimensions. But here, anything can happen. If we have many parameters, the degeneracy can be tremendous and vary a lot from one point to the next. So we were after something that somehow properly does the job. And so here is, after a lot of effort, what we have come with the help of, I forgot to mention my collaborators, apologies. This is a joint work with 2 of my PhD students from the time that I was at TU Eindhoven, Dan Bon and Benjamin Karis, and then we needed the crucial help of Marc Pelletier. They are all from TU Eindhoven. Marc Pelletier is an expert in gradient flows on metric spaces, and this is actually what is going to make the day here, because we are going to introduce a different point of view to understand this problem. So, just to summarize while I am erasing, the drama that we are trying to solve is that with the usual pathway, we cannot guarantee existence of solutions. And in fact, this is going to be translated at the numerics level by some instabilities, which I am going to show you in a minute on the screen. So we would like to kind of solve the problem in a more principled way than beyond having this regularization. So this is point number 3. A metric space approach. As soon as I'm going to say it, it's going to sound quite obvious as an idea. So, in fact, if I consider my set of functions Vn, and I define a notion of distance, which is going to be the distance inherited by the ambient norm, something like this, phi of theta 1 minus phi of theta 2. This thing is a metric space. Okay? It's a metric space because essentially the main crucial thing we want to make sure is that we separate points. And we do because here the trick is that we are no longer really manipulating the parameters. They are problematic because several instances generate the same function. Here we are comparing the functions themselves. And when 2 functions are different really at the function level, this is the crucial thing, even when the parameters are different, right? So that's kind of the crucial idea that is going to be leveraged. And Vn is no, sorry, Vn was the set of neural networks.
So if Vn is less, it is embedded into L2.
It is embedded into L2, but
it's not a metric space. It's Vn with L2 now.
Indeed, it is restricted. It's the restriction. I am no longer going to see any other function in that space. I'm going to focus on that set. And this set, only this thing it's a metric space, okay? Because I can endow this notion of distance, and I satisfy all axioms of being a metric space, okay? It's very trivial. Good. Now I want to define a gradient flow on this metric space. And here comes, after a lot of effort on our part, here comes Marc Pelletier to the rescue, because we were going crazy. I don't belong to the community of gradient flows on metric spaces. We were going crazy in understanding what was the key theorem that we needed to apply to kind of have a definition of the gradient flow, this thing now. I want to define it when, instead of taking u in L2, I take elements in Vienna. Okay, so it is kind of non-trivial because first of all one needs to define an appropriate notion of the time derivative, and what is going to happen is that in order to call the appropriate result, in fact we need that our metric space is not only any other metric space you can encounter in the jungle, it's a complete metric space. And the problem is that this thing, the Vn here, is not closed. Vn is not closed. I am gonna illustrate this to you with this example. So consider this thing, C1 x minus theta 2. Okay. Now I can take the following configuration. I can take C1 equals 1 over a little perturbation. I take the same thing minus the same thing over here, and I take theta 2 being theta 1 minus delta c squared. And I take delta c squared to go to 0. What is going to appear is that I am going to generate a derivative over here of the exponential. In this case, because it's the exponential, I'm going to land in the same space. But if I now take any other function, if I had taken any other function which is not the exponential, I'm going to exit the space Vn, and therefore this set is open. Drama for gradient flow theory. So we needed, to derive this result, actually we needed to derive a result about what is exactly the closure of Vn in L2. And the kind of thing that comes out of this intuition is that to get the closure, to express it properly, we need to take the derivatives and express it kind of properly. Okay, so but to derive the fact that the closure is like the set of neural networks plus the derivatives that we can generate, this is a non-trivial result which is part of the contribution that we have made. And once we have managed to do this, then at long last, at long last we are not through the pain of gradient flow theory, but by identifying, so here's the continuation of the story. I now want to pull ideas from gradient flow in metric spaces, and from this community, they derive trajectories by time discrete marching schemes, which are called JKO schemes. And so we can have a JKO scheme here, which is defined as saying that phi at time n plus 1 is going to be in the arc min of V's in Vn. Now I take the closure, because otherwise I cannot derive my result, of V minus phi theta n squared L2 norm plus the energy F of V. If I manage to minimize this thing, so if I manage to get the minimizer of this thing, I get the phi at the next time step. And in practice, this leads to a minimization problem, because what I'm going to do in practice is to search for parameters in R3n, and so this thing is equal to phi of theta. So I'm going to search for the phi of theta that is minimizing this expression over here. So this becomes a new minimization problem, which actually, and remarkably, is going to come back to be exactly something related to this originally ill-posed problem. If I somehow do well, kind of at the right steps, if I do in the kind of naive approach an implicit Euler discretization, I am going to end up with the same scheme that I am proposing over here. And so the two approaches are gonna be connected in a certain way, thanks to the idea of discretizing at the right place and shifting the point of view to the metric space, okay? And so what happens over here is that the optimality conditions that I'm going to obtain, they are very easy to express and they no longer involve the inversion of this evil matrix. So then, thanks to this, then the positive thing is that yes, we can be and we can exist. There's going to be a solution to this gradient flow problem when I constrain the evolution to be in the metric space of my neural networks by pulling results from gradient flow theory. And the theorem uses language from this field, and basically we can say that every generalized minimizing movement scheme So a generalized minimized movement scheme is the following. I solve this problem, I do a time marching, and I solve this problem for a discrete time step tau. Okay, so this is a generalized minimizing movement. I can take tau smaller and smaller and solve the trajectory again with smaller and smaller time steps. Okay, all of these discretizations are called generalized minimizing movement schemes, and they have a meaning when tau is taken to 0. Okay, so they are generalized minimizing movement schemes. They are a curve of maximal slope. Of maximal slope with respect to something which is called the relaxed slope of f, which I am not going to define because it's absolutely horrendous, and for me, I mean, it has no intuition. So part of the absolute pain of deriving this result was about identifying what was the slope that we had to choose to derive the result. The slope here is somehow the replacement of the gradient here that we take in L2. Now we need to take gradients in the constraint to the manifold. I cannot take variations of my f in the whole L2. I have to constrain it to my manifold. So it's kind of, I mean, you need to redefine what is your notion of gradient. There are several options, and there is where you go absolutely crazy, because there's a whole zoo of this is the relaxed slope, then there is the strong slope, and then in fact none of them were working, so we had to kind of derive something else that eventually helped us conclude that this was the right thing. And so this is, in the language of gradient flow theory, the expression of the fact that I can take this discrete in time scheme, I can take tau to 0, and then there's going to be a continuous time curve which is well defined and which is going to kind of overcome the problem from this. So why have I restricted to 1D and L2? I have restricted it because deriving the result on the closure is hard, and we only know how to do it for this case. And why have I restricted the discussion to gradient flows? It is because the dynamics in metric spaces, as far as I know, we essentially only know a lot for gradient flows. If you give me a Hamiltonian system, no one has a clue how this works. And I would like to show you in the last minutes I have that this derivation is not only like a mathematical gig, that it really reveals that there are instabilities that are connected to the fact that this guy over here is not invertible, and that we are kind of jiggling around with the thing because we don't know how to solve it properly. So here is, okay, good. So here's the example. It's a 1D Allen-Kahn equation. The Allen-Kahn equation is an L2 gradient flow. So it enters fully into our theory. What you're going to see is, it's not properly, excuse me, I need to do the setup a little bit better. What is, here we are. What you're going to see is like the true solution is going to be in blue, and the orange one is the one when we solve it with some regularization over here. Around second 2, there is going to be a jump of the curve around this part, and this can be traced back to the fact that we have to invert this system. The system becomes tremendously ill-conditioned, and then at the numerical level there is this instability. So here we are. So please pay attention to this region over here, and there we go. So the approximation has jumped while the true part had to sort of continue over here, and we can trace it back to the conditioning of this thing being very bad. And it becomes also hard to tweak the epsilon parameter over there. If we use our minimizing movement scheme, I have not the plot, but it is going to work. And I would like to show you another example where we can see clearly the thing doing nonsensical stuff. So here is quite an artificial example. I cannot see anything. Where's the... Okay. I'm gonna close this one. And now, here. Okay. So this is like a handcrafted gradient flow, and we are gonna solve it with the naive approach. What you're going to see is that the bump is going to go down. And we know from the properties of being a gradient flow that the solution, when it reaches 0, it has to continue with the bump in the same location down to the negatives. But what you're going to see is that the scheme is going to produce a bound going to the negatives, but the location of the bump is going to jump. And this is incorrect. It violates the fact of being a gradient flow. Here we are. So that's... And now we are going to jump the bump down to another location, which is not the right solution. Everything coming from this ill conditioning, and if we solve it with this thing, we recover the expected evolution. So with this, I'm going to stop because it's more or less time, and I thank you for your attention.